All right, in this example, I want to do a medical problem. Stats is particularly useful. I feel like this is a timely problem, but this is one that I would do anyways. So what I want to do is I want to consider a rare disease that's present in the population. It's prevalent in only 1/2 of 1% of the population. So 1 out of every 200 people has the disease. And there's a test for it, which says that the test is 99% reliable. What that means is that 99% of the people with the disease test positive, and 99% of the people without the disease test negative, which is very good for a test. So what I want to do is I want to think about the following, and we'll do these in steps. So first, I want to know if you have the test done and it comes back positive, what's the probability that you have the disease? And so I want to calculate what that probability is. And then if you have 2 positive tests, what's the probability that you have it? So we'll do this in order here. So the way I have this set up is that D is going to be the event that you have the disease. X is the event that you do not have the disease. P is that you'll have a positive test, meaning that it says that you have the disease. N is a negative test, meaning that the test says, no, you do not have the disease. So those are going to be our events that we have. And we're going to draw a tree diagram. So you either have the disease or you do not. And then given that, you can test positive or not. So you can test positive or not. Okay. And there we are. So we have the disease or we don't. And we know that it's prevalent in 0.5% of the population, meaning 1 out of 200 people have it. So you can do 0.5%, which would be, so 0.01 is 1%, so half of that is 0.005, which means that 99.5% of the population does not have it. And then it's a 99% reliable test. So the probability, if you have the disease, the probability that you test positive for it would be 99%. And only 1% would you test negative. And then likewise, if you do not have the disease, the probability that you test positive is 0.01 or 1%, with 99% testing negative. So here's our probability tree diagram. And what we want to do is we want to figure out what's the probability that we have the disease given that we had a positive test. So we want to calculate what's the probability that we have the disease given that we had a positive test. I just realized that I'm using P in 2 different ways here, but hopefully that's clear enough. This P stands for probability. This P on the inside is the event that you have a positive test. So I think that's okay. So we want to know the probability that we have the disease given that we had a positive test. And to do that, we'll just apply our formula. And we can do this one of 2 ways, but I think it's easiest to do this with Bayes' theorem. So the probability of D given P will be the probability of P given D times the probability of D divided by the probability of P. And so we need to think about what's the probability that we had a positive test given that we have the disease. And so P given D is going to be 0.99. That's what this number here represents, is exactly the probability of P given D. And then we'll multiply that by the probability of D. So that's going to be 0.005. And then we're going to divide that by the probability that we test positive. So remember, there's 2 routes to get to a positive test. We can either have the disease and then we test positive, or we don't have the disease and then we test positive. And so we have to multiply all the numbers along each path to P and then add them up. So we're going to get 0.99 times 0.005 plus 0.01 times 0.995. I did not leave enough room here, but I can cheat just a touch here. So this is 0.01 times 0.995. And so if you crunch the numbers, it turns out the probability that you have the disease, given that you have a positive test, is 0.3322, or about 1/3. Okay, so it's an approximately 1/3 probability. So what I want to do then, let me make sure I did that right. Yeah. So what I want to do then is I want to, just before we go and answer the second question, this seems really low, given that we have a really high reliable test. The fact that we have a positive diagnosis still only means that there's about a 1/3 chance that we have the disease. Now that's worse than the 0.5% chance that you have the disease just by knowing no information, by picking randomly someone out of the population. But what I want to do is, let's think about this. So let's say we have 1,000 people. So we have a sample of 1,000 random people. And the way that we're going to do this is we know that 0.5% of the population, or about 5 people, so about 5 people have the disease. And that means that the rest do not. So 995 people do not have the disease. Okay. Now, of the 5 people with the disease, okay, so of the 5 people with the disease, 99% of them, in other words, 5, are going to have a positive result for the test. So there's going to be 5 positive tests. So we would expect 5 times 0.99, so 4.95 positive tests. If I had 1 million people, we could be a little bit more careful with the numbers, but this is just to kind of get an intuition anyway, so we don't have to be that careful. Of the 995 people in the population that do not have the disease, how many positive tests and how many negative tests are there going to be? Well, we know that 99% of the people that do not have the disease will have a negative test, but that means that 1% of the people without the disease do have a positive test. And what's 1% of 995? Well, it's 9.95. So let's say that there's 10 positive tests. That means that there's 985 negative tests. And now what we're going to do is just consider the positive tests. We have 15 of them. Okay, so of the positive tests, we have 15, 5 of which are from the people with the disease, 10 of which are from the people without the disease. And that means that the probability that you have the disease, given that you have a positive test, is about, this is not exactly equal, but about 5 over 15. And it's about 1/3. That actually checks out, the math checks out there. So that's the intuition. The reason why the number seems strange is because it's such a rare disease, it's not very prevalent in the population. So that means that the number of positive tests can be skewed towards the people that don't have the disease just because it's so rare. Most people don't have the disease, therefore that could skew the numbers a bit. So that is how that works. What I want to do though is I want to calculate now. Let's do a second test. So what we're going to do is we're going to go back to our example, and let's say that we have a person that's tested positive for it. There's a 0.332 there's a 33.2% chance that the person has the disease. And now let's go back and let's do the disease again, or let's do the test again and see whether or not that changes the probability. This is in statistical terms is called updating your priors, because what we're doing is we're changing the prior assumption of whether the person has the disease or not, whatever that probability is. So we're going to do the same tree diagram, and I use the same letters. So D is going to be that we have the disease, X is that we do not, And then given that we have the disease or that we don't, we can test positive or negative. So we can test positive or negative. And so now let's think about what's the probability that we have the disease. Well, that's what we calculated before, is 0.3322. And this is the updating the priors that I was just talking about. Knowing more information changes a probability, and that can change the outcome. So in our case now, the probability that we have the disease is about a third, about 0.332, which means that the probability that we do not have the disease is 0.6678. And then the test is still 99% reliable. So if we have the disease, there's a 0.99 chance, a 0.99 probability that we test positive and a 0.01 probability that we test negative. And likewise, if we do not have the disease, there's a 0.01 probability that we test positive and a 0.99 probability that we test negative. And so now the probability that we have the disease, given that we have a positive test, is going to be the same as before. It's going to be the probability of P given D times the probability of D divided by the probability of P. And so what's changed now is the probability of D and X. So P given D, that probability is still 0.99. The probability of D is going to be 0.3322. And I can already tell I'm going to run out of room. And the probability of P, we're again going to think about all the routes to get to P, so we can either have the disease or not. So that's going to end up being 0.3322 times 0.99 plus 0.6678 times 0.01. And then let's plug this in, and I'll have you check my numbers here. But this is 0.99 times 0.3322 divided by 0.99 times 0.3322 plus 0.6678 times 0.01. And that'll be the probability that we have the disease given that we have a second positive test. Okay. And so that's going to turn out to be 9.98.9800987. So let's just say 0.9801. So that's the probability that we have the disease given that we've had two positive tests. Okay, so that's how that's going to work. So knowing just one positive test gave us a probability of about a third, but now we can be pretty certain that we have the disease given that we have a 9.98 probability that we have the disease given a second positive test.